Hello and Assalamualaikum everyone. Good morning. Okay, so can you guys hear me clearly? Can just respond in the chat. All right, okay, great. So in case my internet connection or any the meeting is breaking, so please let me know. Okay, right? So I hope everyone is doing fine and well wherever you are. Okay. All right. So let us begin our first discussion session. Okay, so we're just going to go through some of the examples that we discussed in our lecture and also our exercise one. Okay, so first up, okay, so let us go through example 2.1. Can everyone see my iPad screen? All right, okay. So these are the example that I asked you to submit on Elen. So thank you all for submitting. So I'm just going to give you the answer. Okay, so you can check your submission. That one will not be graded. Okay. So the first question is you need to compute the probabilities that there are exactly 0, 1, 2, 3 customers that will arrive during a 5-minute period. Okay, so for question A, sorry. So for question A, first is the probability of n equals to 0. Okay, so you just substitute in your equation. So you should get 0.1353. Okay. The second one is n equals to 1. So you should get 0.2707. And then n equals to 2, you should get 0.2707 as well. And then n equals to 3, you should get 0.1804. Okay, so check and confirm your answer. So for question B, okay, so probability of there being more than 3 arrivals. So your n greater than 3, so what you have to do is 1 minus the complementary event, 1 minus probability of n equals to 0 plus probability of n equals to 1 plus probability of n equals to 2 and then plus probability of n equals to 3 that you calculated earlier in part A. Okay, so you should get 0.1429. Okay. So that is on question, example 2.1, right? So moving on to example 2.2. So is everyone okay with example 2.1? Right, okay. So let us move on to example 2.2. Okay. So A, you want to calculate probability that a given service time is less than 1 minute. So probability, so A, probability of T less than 1 minute. Okay. Make sure you use the right unit for your service time. Okay. So T less than 1, so substitute in your formula. So you should get 0.4512. Okay. B is probability. Okay, the service time is less than 2 minutes. Okay. So you should get the value of 0.6988. Right? And then C, probability more than 2 minutes. So you should get 0.3012. Okay. So that is for example 2.2. Okay, so you can check your answer that you submitted on e-learn. Okay, in case you have any problems, so you can just let me know. Right? Okay, so everyone clear on example 2.2? So you basically just substitute the value. Okay, your t is equals to 1, 2, and 2 depending. Okay, so t less than 1, t less than 2, and then t greater than 2. Okay, so for continuous, okay, I want to ask you, what is the probability of t equals to 1 for continuous distribution? What is the probability of t equals to 1? Anyone? Okay, because here we have t less equals, okay, but here we have t less than 1, okay. So what is the value of t equals to 1? Okay, anyone?
Doctor, I think
Yep.
it will be zero.
Yes,
Zero.
true. Okay, so that's why we can substitute. Who is that? Who's speaking just now?
Copying, Tang
All
copying.
right, okay. Thank you, Koping. So it is actually equals to 0. So that's why you just substitute, because it is the same, because this is the case of continuous probability distribution. Okay. So next, let us move on to our example 3.1, okay, that we learned last week. Right, so the first thing, okay, for example 3.1, okay, so A, you have to draw your transition or rate diagram. Okay, so this one I already provide to you. Okay, so based on your arrival rate and also service. Okay, so since this is your transition diagram, so first you need to define. Okay, so in our lecture we learn using the state I. Okay, so refer to your question. So if it gives you the state is in N, so you have to define your state N, right? So this is your transition diagram. Okay, and then question B, you have to write the balance equation. Okay, so the rate in equals to rate out, right? So continue writing up until state 4 and 5. Okay, so for state 4, so you should have, 0, 1, 2, 3, state 3 first, okay? So for state 3, okay, so you should have lambda over 2 pi 2 plus mu pi 4 equals to lambda over 3 plus mu pi 3. Okay. So for state 4, you should have lambda over 3 pi 2 plus mu pi 5 equals to lambda over 4 plus mu pi 4. Okay, finally, your state 5, lambda over 4 pi 4 equals to mu lambda 5. Okay, so that is for question B, right? And then question C, so you have your lambda equals to 20 and your mu equals to 10. Okay, so you just substitute the value in your rate diagram. Okay, and then, okay, so remember, okay, what you have to do first. So first, the important thing is you need to find or express your pi I or pi n in the terms of pi node. Okay, so this is step number 1. Okay, so step number 2, okay, what you have to do is have to determine your pi node. Okay, so first, okay, I already give to you. So for pi 1 and pi 2. So for your pi 1, okay, so you should get 2 pi node. For your pi 2, you should get 4 pi node. So did anyone try and calculate for pi 3? What did you get for pi 3? Did anyone attempt to calculate pi 3? Probability of the system being in state 3.
Doctor, I
Yep.
got 4 pi naught.
4 pi naught. All right. Thank you, Mushida. Okay, so for pi 3, you should get 4 pi naught. Did you calculate for, Mushida, did you calculate for pi 4 and pi 5 as well? What did you get?
Yes, doctor, I got 8/3 pi naught for pi 4.
Okay.
And pi 5, I got 4/3 pi naught.
All right. So thank you, Mushida. Okay, so this is what you should get for your pi 3, pi 4, and pi 5. So 4 pi naught, 8/3 pi naught, and also 4/3 pi naught. Okay, so how are you going to calculate? Okay, so your pi naught is equals to 1/1 plus the summation of your Ci for I equals to 1 until 5. So this is the value that you should get, which is 1/15. Okay, so next, moving on, okay, to our next question. Okay, so after you have get your pi naught, okay, then only you can determine your L, LQ, your W, and WQ. Okay, so for your L, so did anyone manage to get the answer for your L? All right, okay, Lukman. L 2.622. Do you want to continue for LQ as well? Okay, so 1.689, right? So did you calculate for W and WQ as well? All right. 59 over 190. Okay, so your WQ 1 over 1/5. Okay, so what is the value of your your lambda bar? 76 over 9. All right. Okay, so thank you, Lukmano. So did everyone get the same answer? Did anyone get a different answer? So for your W, you use L over lambda bar, and for your WQ, you use LQ over lambda bar. So did everyone manage? First, you have to calculate this value first, okay? So n equals to, what did I give you previously? Right, so n equals to 0, the summation of n equals to 0 until 4. Okay, so your lambda n pi n, because we use state n here. Okay, so 76 over 9. Okay, in decimal, what should we get? 8.44. Okay, so did everyone manage to get this value? Same. Okay, so did everyone manage to get the same value? Right, okay. All right, okay. So, and then you calculate for your W, okay? So Y, we only consider, okay, arrival rate until your N is equals to 4, because N is the only state, okay, that the customer is still allowed in the system while your waiting line, okay, while there are 4 customers waiting, okay, one being served, state 5, okay. So while there are still 4 customer in the system, oh sorry, not waiting line. While there are still 4 customer, up to 4 customer in the system, that is only when your potential customer from your calling population is allowed to enter the system. Once your state reach the state 5, where your n is equals to 5, there are no arrival rate. Okay, so because your lambda 5 is equals to 0 because the customer is not allowed to enter anymore. So that's why, okay, so for your lambda bar, we only consider the case for n equals to 0 until 4, right? Okay, so that is why we get, okay, so for our, for our W, so you just take the value of L, 2.622 over 8.44. So you should get 59 over 190, or you can express it in decimal points. So you should get 0.3105. Oh, sorry. You should get 0.3105, and your WQ is 0.2, right? Okay. So that is all for example 3.1. Okay, so L, LQ, W, and W, Q. Okay. So is everyone clear in for example 3.1? Everyone okay before we move on to our exercise 1? Right? Okay, good. So for exercise 1, okay, so question 1. Okay, so I'm going to skip question 1. You can try and prove that yourself. So let us move on to question 2. Okay. Sorry, give me 1 minute. Okay, so let us move on to question 2. So for question 1, you can attempt, okay, you can show on your own. So if you want me to check, so you can just forward your solution to me. So let us move on to question 2. Okay, so you have a single server queue. Okay, so basically you have one server, okay, that has exponential inter-arrival and service time with mean of 1 over lambda, and that is for inter-arrival, and then for service time you have 1 over mu. Okay, sorry, right? So you have 1 over mu. Okay, so suppose that the new customer are sensitive to the length of the queue, so that if there are I customer in the system, when the customer arrive, then the customer will join the queue with the probability of 1 over I plus 1. So otherwise that customer will depart and does not return. So what you have to do here is you have to draw the transition or rate diagram and also find the steady state probability distribution. Okay, so did anyone want to share their solution? So I'm going to stop sharing. So now is your time to share. So did anyone want to share their solution for exercise 1, question 2? Anyone want to give a try? No one. Okay, so let us start with Afif. So did you attempt question 2 for exercise 1? Afif, are you there? Can you hear me?
Yeah.
Yeah. Okay, so did you manage to solve for question 2?
Tu saya tak buat.
No.
Saya buat 1, 3, 4.
1, 3, 4. Alright, so you did not manage. So anyone managed to get a solution for question 2? What about let's see. What about Keng Hui? Chang Keng Hui? Did you manage to solve for question 2?
Yes, but
Or
not correct or not.
okay, so you can share. Never mind, we can go through it together. Can you share? Did you have it in PDF?
Yeah.
All right, okay. So you can share and then you can explain.
Okay. I need to log in the email.
All right, okay. So we'll wait for Kang Hui for a while. Okay. So never mind if you cannot finish up until question 4, we can continue next week. So that should be okay. Right. Okay, so for the rest of you who did not attempt, so first thing that you have to do is you have to define your state. Okay, so please define your state. Okay. All right. Okay. Okay, so you can maybe you can zoom in a bit. I can see, but not sure if your friends can. Can everyone see? All right, yeah, that's better. All right, so you can explain.
So let I equals to the number of customer in the system, and then it says that I when the I probability is the what the then I just use I equals to 0, then the customer will join the queue will be the probability of I plus 1 to the power of -1. Then I use such that I equals to 1, then the tick is the customer will join the queue, and then the probability of one customer, the probability is 1/2, and then the number of customer is 2, the probability is 1/3, and then so forth. And then I proceed to the transition diagram, and then this is my attempt, the steady state probability distribution. So
Sorry. Hang on.
sorry,
Which one is question 2? I think I'm looking at the wrong question. Question 2 is lambda with the inter-arrival and service time equals to 1 over lambda, right?
yeah, 1 over lambda.
Okay. All right. Okay. So how did you get this is question 2. All right. Okay. So why did you stop at state 3?
I cannot find the final thing.
All right. Okay. So never mind. Okay. Thank you, Kang Hui. So let us discuss. Okay, for this question. Okay. So you have your state, right? Okay. So first you define your state I. Okay. You define your state I, the number of customer in the system. Okay. So then you have the information. Okay. The inter-arrival and service time. Okay. You have the mean of 1 over lambda and 1 over mu respectively. Okay. So I'm going to okay, Kang Hui, thank you. So good attempt. Okay, but there are some correction that we need to make. Okay.
Thank you.
All right, thank you. So let me share again. Okay. All right. Okay. So first you have to define your state I. Okay. So you have to define your state I. Right. So next, the information that you have is the mean is equals to 1 over lambda and 1 over mu. So what is your arrival rate? What is your arrival rate and service rate if the mean is equals to 1 over lambda and 1 over mu? Okay, so your arrival rate is lambda and your service rate is mu. Okay, and the next information that you have, okay, so that the new customer, so if that customer join when there are I customer in the system, okay, so first you will begin with state 0 and then state 1, state 2, 3, 4, okay, and let's see if we have more. Okay, so when the customer arrive, okay, your new customer arrive, so there are already I customer in the system. Okay, so when there are already, for example, when you have one customer in the system, okay, when you have no customer in the system, so state 0, so what is the arrival rate? So your arrival rate is lambda, but the probability that the customer will join, okay, is 1 over I plus 1, where I is your state. Okay, so what you have to do is you have your arrival rate lambda, but the probability that the customer will join, given that the system is in state 0, is 1 over 0 plus 1. Okay, so which will give you the value of lambda. Okay, so when there are one customer in the system, okay, so the probability that the customer will join, okay, so you have your arrival rate lambda. So the probability that the customer will join will become your I is equals to 1, 1 plus 1. So you will get lambda over 2. Okay. And then for your arrival rate when the system is in state 2, okay, you substitute, so you will get lambda over 3. And when in state 3, okay, so you will get lambda over 4. Okay, so where do we stop? Our state. Where do we stop? Is there any restriction? Or is there anywhere in the question that mention that the customer will not join when you have a certain number of customer in the system? Okay, so where do we stop? So anyone? You can just type if you don't want to unmute. So where do we stop for our transition diagram? Our state can take up until what value? Your I. I know, care to try? I know, can you hear me?
Yes, Doctor.
Yeah, so your state, your value of I. So now we have until 4. So what is the value of I? Like previously in example 3.1, okay, so you have your n up until 5. But in this question, does it mention to you the value of I until when? Or any condition that whether the customer will not enter the system when there are certain number of customer in the system?
From what I know, no, Doctor.
For your I, the value of the state, okay, the value, this value. Okay, so up until when can it take? Sorry. Your value of I. No idea.
No idea, Doctor.
All right,
Because
okay.
in the question said that otherwise he or she departs and does not return.
Otherwise, okay.
He or she departs and does not return.
But that refers to the probability of the arrival. Okay, so, all right, so never mind. Okay, so we have one answer from Mushida, which is infinity. Okay, yes, okay. So the state, okay, continue. Okay, hang on, my iPad just start to disconnect. Hang on. Right? Okay, so it should be, okay, up until infinity. Okay, so wait, I think I need to stop sharing for a while. Okay, so it should be up until infinity, like your general birth and death diagram. Okay, so Moshida, did you get the did you draw your transition diagram up until infinity?
No, doctor. I got like Kenghui just now.
All right, okay. So did anyone draw their transition diagram up until infinity, like the general birth and death? Because there's something wrong that I cannot share my iPad. So did anyone manage to draw the transition diagram? Similar to your general birth and death process, but you have your arrival rate, okay? Different, okay? So you already have the value of your arrival rate. We haven't looked at the service rate. Did anyone manage to get the right transition diagram? So it should continue until infinity like your general birth death transition diagram. Am I talking to myself? Does anyone wants to respond? Chen Yi, how does your transition diagram look? Yeah, how does your transition diagram look? Yep.
Do you see my PDF?
Yes. Can you zoom in a bit? Small. Mm,
So I can speak on like
yeah, okay. So, okay. So actually it should continue. Now that is when you limit until I, right? So you can just after state 4, you can just ... because we don't know, okay? Up until when? Okay, so all right, so you have your lambda node equals to lambda over 2, lambda over 3, and so on. Okay, good. So for your mu, okay, since you only have one server, okay, so the value of your mu I is equals to mu. Okay, so it's not, you only have one server. So when the system is in state 1, okay, the service rate is mu. State 2, the service rate is still mu because there's only one server that can attend to one customer and another customer have to wait. Okay, and then so on. Okay, so for your mu, okay, the value for your mu I, okay, for all of the state is equals to mu, right? Okay, so can you scroll down a bit? Did you get the steady state? No.
no.
No, all right, okay. So this is how your diagram should look like. Okay, so next what you have to do is you need to form your steady state equation. Okay, so let us try and form that. Okay. So thank you, Chen Yi. So you should have this.
Thank you.
All right, so you should have. Let's try. Okay, so if I can start sharing again. Can you guys see now? Right? Okay, so sorry about that. Not sure what happened. Okay. So, okay, so you should have, okay, up until infinity for your service rate, okay. So it should just be mu because you only have one server, okay. So next what you have to do, okay, so you can write down your rate in equals to rate out. So the first equation you should have pi naught lambda equals to pi 1 mu. And second equation pi 1, okay, you can factorize, okay, plus mu equals to pi naught lambda plus, sorry, pi 2 mu, okay, and then so on, like your general birth death, okay, but now you already know the value of your lambda I. For your mu, okay, for your mu I is equals to mu, okay, for your I, but for your lambda I is equals to 1 over I plus 1 lambda. Okay, for your I equals to 1 to until infinity. Okay, so next what you have to do is, okay, so express your pi I in terms of pi naught. So for your pi 1, you should get lambda over mu pi naught. For your pi 2, you should get, okay, so please double check, over 2 mu 2, mu to the power of 2, okay? So here is lambda square, okay, over 2 mu square pi naught, okay? And then for your pi 3, you should get lambda to the power of 3 over 3 times 2 mu to the power of 3 pi naught. Okay, so then by induction, okay, continuing from there, you should be able to show that your pi I is equals to lambda to the power of I over I factorial mu to the power of I pi naught. Okay, because if you try to find for pi 4, you should get lambda to the power of 4 over 4 times 3 times 2 mu to the power of 4 pi naught. Okay, so basically you can just write down, okay, your 3 dots. Okay, so for pi I, you should get this equation. Okay, for your pi I. So next, what we have to do, we have to find our pi naught. Okay, so in order for us to determine our pi naught, so we need to use the sum of your probability of being in state I. Okay, so pi naught plus pi 1 plus pi 2 equals to 1. Okay, so what you have to do is, over here you will have lambda over mu pi naught plus lambda square over 2 mu square, okay, plus lambda to the power of 3 over 3 times 2 mu to the power of 3, okay, and so on should be equals to 1. Okay, so how we can simplify is, remember that we have learned about our traffic our row value. Okay, so we can substitute, okay, our row equals to lambda over mu. Okay, so it's up to you whether you want to use this general form, or you can decide to substitute your row equals to lambda over mu. So if you were to substitute, okay, so you should get here, okay, sorry, I think I left out the terms pi naught here. Okay, so you should have pi naught here. Okay, so if you substitute your row equals to lambda over mu, you should have row pi naught plus, okay, also, sorry, here should have pi naught plus, okay. So you should have pi naught plus row pi naught plus row square over 2 factorial. Okay, 2 factorial is equals to 2. Okay, so we're writing it in general form. So pi naught. So then you will have row to the power of 3. Okay, 3 factorial pi naught and so on. Okay, so equals to 1. So next what you have to do is you factorize your pi naught because we want to find our pi naught. So 1 plus row square over 2 factorial plus row to the power of 3 over 3 factorial, okay, equals to 1. Right? Okay, so then you will have your pi naught, okay, equals to this equation here, okay, to the power of negative 1. Okay, so which, okay, is actually equals to e to the power of negative rho. Okay, so this one you can check, right? So it is actually equals to e to the power of negative rho. Okay, so then, okay, so you have get the value of your pi naught. Okay, so you have get the value of your pi naught. Okay, so you can substitute your pi naught in your general form of pi I. Okay, so for your pi I, you should get equals to rho to the power of I over I factorial e to the power of negative rho for your I equals to 1, 2, 3, and so on. So that is your solution for question 2. Okay. Right. So you need to determine the value of your pi node first, and then you can express it, or you can express your pi I. Okay. So the steady state probability distribution for your queuing system. Okay. So you should get this value, right? So if you get this value, good. Okay. So if not, you can try and write down, okay, one by one, okay, because this is more of a general birth-death process, okay, where you have, where you know, okay, in general birth-death, so your arrival rate for each state is different, okay, and it can also be the same, okay. So if you get the value, then you just substitute the value and try to solve for your pi node in order for you to determine your steady state probability distribution, right? Okay. Right, so never mind. If you have any questions, so you can ask me, right? So next on question 3, okay? So for question 3A, so you have to draw your transition diagram. Okay, so did anyone want to share their transition diagram for question 3? Anyone want to share? Afif, just now you mentioned that you attempt question 3. Can you share?
Boleh.
All right, thank you.
Nampak?
Yes, I can see.
Ni transition diagram dia tu.
All right. Okay. So you have your state until, where's your state 0? When there are no customer in the system.
Kena buat juga.
Yes, you need to consider state 0 as well. Okay. So then you have state 1, 2, 3, 4. Okay. So why until 4? Why only until state 4 for your I? Because if a potential customer arrives and find out that there are 4 customers in the queue, he or she will leave. Is that why? Is that why you write down your state only until the value of 4? Is that why your I until 4?
Sebab dia, if a potential customer arrive and find out that there are 4 customers in the queue.
Right. So if there are 4 customers in the queue, how many customers are being served? How many server you have?
How many server?
Yeah. You have 4 customer waiting. So if there are customer waiting, so basically all of your server are busy, right? So how many server you have in the system? 1 server. Power said 1 server. Atira said 2 server. So what do you think, Afif? How many server you have?
1 server.
1. Why is it 1 server? Because the question mentioned that the post office is handled by 2 clerks.
Maksudnya di 2 server.
Yes, okay. All right, okay. So never mind, it's okay. Okay, so you should have 2 servers. So if you have 4 customer waiting, so another 2 customer. you should have another 2 customer, okay, being served, right? Did you say something?
No.
All right, okay. Okay, so be careful, right? Okay, so thank you, Afif. Okay, so I'm going to guide you on how we're going to get our transition diagram. Okay, right, thank you, Afif. Okay, so please be careful and read the question. Okay. All right, so let us try and draw our transition diagram for question 3. Okay, so first you can define your state. Okay, I is the number of customer in the post office. Okay, and then you need to start with state 0 when there are no customer. Okay, so it is mentioned that if the potential customer arrive and find out that there are 4 customers waiting, so you know that you can have 4 customers waiting maximum, because the potential customer will leave if you have 4 customer waiting. And if you have 4 customers already waiting, okay, waiting basically it means that all of your servers are busy. Okay, so you have 2 clocks. Okay, so basically you will have until state 6. Okay, 4 customer waiting and then 2 customer being served by 2 of your server. Okay, so then you can determine your arrival rate and also your service rate. When there are 6 customers in the system, okay, the customer, your potential customer will not enter anymore. Okay. Okay, so then you can determine your lambda and also your mu. Okay, so if you have, let us look at our mu first. If you have 2 server, when there are 1 customer in the system, only 1 server will serve the customer or will do their work. Okay, so you will have your rate of mu. Okay, so your mu1, okay, should be equals to mu. So what is the value of your mu here? The service rate for each customer follows exponential distribution with mean of 10 minutes. So your mean is 10 minutes. Okay, if we were to substitute, okay, in the unit hour, if we want to use the unit hour, okay, so your mean is 1 over mu equals to 1 over 6 per hour. Okay, 10 over 60. So your mu, you should get equals to 6 per hour. Okay, so your mu1, when you have 1 customer in the system, okay, so only 1 clerk is doing his or her job, so your mu is equals to mu, which is equals to 6. But when you have 2 customers in the system, okay, both of your server or clerks, okay, will do their job, okay, so your service rate will become 2 mu, okay. Sorry. Your service rate will become 2 mu. So what about when we have 3 customers in the system? What is the service rate? It is still 2 mu because you only have 2 servers. Okay, it will not be 3 mu because you don't have 3 servers. Okay, so the same for state 4, state 5, and state 6, right? Okay, so next is your arrival rate. Okay, so your arrival rate is 15 customer per hour. So your lambda is 15 customer per hour. Okay, if there are 2 customer waiting, the arrival rate will decrease to 9 customer per hour. Okay, 2 customer waiting basically means 2 customer being served. Okay, so that is in state 4. Okay, so your lambda 4, when you have 2 customers waiting, it means 2 customer being served, so your lambda 4 will decrease to 9. Okay, so for your lambda 1, lambda 2, lambda 3, lambda 4, okay, it follows the value of your lambda, which is 15 per hour. Okay, it will only decreases to 9 when you have 2 customer waiting. So remember, it's not 2 customer in the system, it is 2 customers waiting. So when 2 customers are waiting, so there are 4 customer in the system because you have 2 servers, right? And then if there are 3 customers waiting, the arrival rate is 5 customer per hour. So your lambda 5, sorry, this should be lambda 0, 1, 2, 3. Okay, sorry about that. Right, so lambda 5 is equals to 5. Okay. So now we have our value of all of our arrival rate and also service rate. Okay, so next you can try and solve for probability that the customer arrive and finds out there are at least one of the clerks is idle. Okay, so first thing that you have to do is you need to find your pi note. Okay, you need to express your pi 1, pi 2. Okay, do the same up until you should have pi 6. Okay, and then express everything in terms of pi note and then determine your pi note, right? Okay, so find your pi note, okay, equals to what, and then find your pi I as well, okay, for pi 1 until pi 6. Okay, so for question B, what do you actually have to find? Find the probability that there are the customer arrive and finds out that at least one of the clerk is idle. So what value do you have to calculate for question 3B? Howell, what value do you have to calculate for B, question B?
The value of pi 3.
Pi 3. Question B. So pi 3, basically the system is in state 3. There are 3 customers in the system, right? If pi 3, so you have 3 customers in the system, does it mean that your clerk is, your server is idle?
Oh no.
No,
It's
all right.
pi
So you
pi
actually
1.
have pi 1.
Pi 1.
Okay, pi 1, is that all?
Yeah,
At least one. At least one
at
is
least
idle.
one.
Yeah.
Dengan pi note.
Yes, okay. So for question B, you have to find, okay, the probability of the system being in state 0 and state 1, because that is when at least one of the clerk is idle or not doing anything. Okay, so for question B, you find pi note plus pi I, pi 1, okay. And then for question C, what do you have to find? Okay, I want you to attempt this and then we will discuss the answer next week. Okay, so for question C, what do you have to find? Average number of customer waiting, the customer in the waiting line. So what do you have to find? For question C. Jack, for question C, what do you have to find?
Good morning, Doctor.
Yeah, morning.
We have to find the average number of customers in queue.
Yeah, how do we find that?
We use the formula LQ is equal to summation of I equal to 3 up to 6.
All right, okay. Thank you, Jack. Okay.
Okay.
So for question C, you have to find I equals to 3 until 6. Okay, this is your I minus your C. Okay, pi I. So how many server you have? You have 2. So it is I minus 2. Okay. Oh, okay. I just read the chat. Okay, Mushidah and Ain. Okay, yeah, you have to find LQ. Right, so try and solve for question 3. Okay, so next week, okay, we will check the answer for question 3 and then we will discuss question 4 as well. Okay, so if you have any questions, you can WhatsApp me personally. Okay, so most of your friends from OR group should have my phone number since we don't have a WhatsApp group. Okay, so you can ask them for my phone number if you want to WhatsApp me personally. Okay, so I will try and help you out. Okay, so next week we will continue. Okay, discussing the answer for question 3 and also question 4 and any example, okay, that I ask you to do in the lecture notes, right? So that is all for this week. So I'll see you guys again next week. So tomorrow I will upload the materials for this week. Okay, so your lecture 3 part 2, right? Okay. So thank you, everyone. I'll see you again next week. Take care.